bit delayed because the work is too much right now, especially of office also. So yeah, the problem simply says that we are given an integer array. It's very short and simple problem. Integer array nums, and we are also, when we have to return an integer array called as counts, where counts of I is the number of smaller elements to the right of my nums of I. What he mean by it is, let's say for example, for this number 5, I have to return this count array. What this count array means, after this 5, which means in the right of 5, how many elements are smaller than 5? I can see they are 2 elements, 2 and 1. So for 5, the answer is 2. 2 and 1, count is 2. For example, same way for 2. For number 2, count of smaller elements to the right of 2 is just 1. Okay, answer is 1. Now same way for 6, count of smaller element to the right of 6 is just 1. Okay, answer is 1. Same way for 1, count of smaller element to the right of 1 is no 1. So answer is 0. So you can see that you can simply solve, and you want to figure this out. Now, first, very brute force, basic ways. Okay, I'll do one thing. I am at this index. I'll go. I know, okay, it is my ith value. I know nums of I, what is it? I'll go on from I plus 1 up till the end, which is the n. And then I will see whosoever is lesser than my nums of I, I'll keep on increasing my count. Okay, I'll put the count as count of I. And then the same way, if I am at the next index I, I'll again go. The next index I, I'll again go. So for every index, you are again going on up to the super end. For every index, you are going on the super end. So every index, which means n indexes you have, you are going to super end. Again, for every index n, every index n. So you have n indexes, and for every index, you are going n, iterating the entire from I plus 1 to j. So that will be O of n square, and very easily we can see O of n square will never work. So now we know one thing. Okay, I know O of n square would not work. So what's the next thing? For sure, O of n log n. O of n log n. Again, O of n is a very good case, but yeah. Next thing, okay, O of n square is not working. So next thing which we can think of is O of n square. Sorry, O of n log n. Now, O of n log n, for sure, as soon as we hear O of n log n factor usually comes by 3 things. Either it's a Fenwick-Tree or a segment-tree like question, or it's a simple sorting, which we can do. Maybe it's a greedy kind of problem, or it is binary search. So you can also interpret this as the same way. So it is more or less either you are applying a Fenwick-Tree or a segment-tree or a binary search or a sorting. Now, for sure, if you had watched the video of Fenwick-Tree, again, if you have not watched it, please go and watch this video. It is a complete explanation of a Fenwick-Tree with the proof of everything in very detail. So now, if you have watched this, so you remember a Fenwick-Tree, usually in a broad level, I can see it helps us in finding the range sum, in log n time. But Aryan, I don't want to find the range sum. I want to find the count of smaller elements. That's not a range sum. Bro, that's an issue. We have to convert the problem. We know that this is the problem. We know this is the answer. So we have to convert the problem that, okay, I have to figure out the number of elements to the right. Now, I want to figure out number of elements. Okay, if this is the element, number of elements to the right of him, which are smaller than my current element 5. So can't I do one thing? What if I would have gone in the increasing order itself, which means firstly I would have populated 1, which means, okay, I will encounter the smallest element 1, then I will go and check the right sum. Again, I can easily find the range sum in the right part. So as soon as I encounter 1, I'll put a 1 value. Okay, 1 I encountered once, 2 I encounter 1. Now you will see I can simply go and find the range sum in the right part. Oh, maybe, which means that it gives us a hint. Okay, next bigger element is 5. As soon as I put a 5, like, okay, I encounter a 5, I'll do a range sum in the right part of 5. Oh, so the problem itself can help us say that, okay, what I can do, I want to find the count of smaller elements. So rather than saying count of smaller elements, I will go in the order of smaller elements itself. Firstly, I'll go on to the smallest, then bigger, then bigger, then bigger. Then I know, okay, if I'm going on in the order of the elements from smaller to larger, I can simply say that, okay, bro, I know that this is a smaller element, which for sure, I'm going in the order. So if I want the smaller elements to the right, so I know one thing, that I have been going in the order itself. So all the elements to the right, which have 1 marked, which means they are smaller than me, and I want to count only. So I can simply do a range sum of this portion, and I know the range sum because of Fenwick tree or a segment tree is just O of log n. Although I don't much prefer segment tree over a Fenwick tree because a Fenwick tree code is very small. It is like a DSU code. How big the DSU code is, that big is our Fenwick tree code. So it is easily writable in an interview. But a segment tree code, it is not writable. That's the reason I usually prefer a Fenwick tree. But now we have got the intuition that, okay, bro, I'll do the exact same stuff. That I have this nums. I know in my Fenwick tree, I make a bit binary index tree array. But okay, remember one thing from the video, that always your BIT array is one base indexing. That is one thing I stressed a lot, that make sure that you don't confuse in the values of bit, because usually you do I and minus I and all that stuff in your Fenwick tree. So be consistent that your bit is always one based. Now we know that we have the idea of how things work. We'll simply keep on populating, but we'll simply make sure that I'll populate one based. Now I said one thing, I'll populate and go in the order of smaller to larger. So I will firstly grab these elements. I will simply sort these elements. Now all the elements are sorted. 1, 2, 3, 1, 2, 5 and 6. But make sure, if I have sorted it, I also need to keep track of the original index. R and Y is index in it, because bro, at that index only you have to populate that. Okay, I have found a 1 because 1 is at index 3. For me, significance of index is very important, because for 5, here he is at index 0. For him, the right indexes are 1, 2, 3 and so on and so forth. For 2, its index is 1. So for him, the right indexes are 2, 3. So for me, values are also important and the corresponding indexes are also important. So I will keep a pair of value and index and then sort my values. Now I have got this specific sorted vector of pairs in which I have value and the corresponding index also. Now I will just go on in my bit. How I will do it? Simple. I know that this is the first element which I will encounter. I know its index is 3, but my bit is 1 based. So I will increase the index. I'll make it a 1 based indexing. So 3 will become a 4. Index now is saying as 4. I know, okay, I have encountered one element. Again, for me, element value is not important. I want the count of values. And for me, count is nothing but range sum. I'll have to say range sum. So for every element, I will say, okay, bro, I have got one element here. So I'll just say count is 1. I'll say count is 1. Okay, one element I've got. What will happen? Okay, one element I've got and its count is 1 and that's it. So in your bit form, in your actual bit code, which means Fenwick tree code, you will simply say update value as 1 at this specific index, which is existing index, which is ID plus 1, because I know my bit array is 1 based. So you will see exact same stuff, that firstly in the code itself, you will simply have a bit array, which you usually make for a Fenwick tree. Then you will make a pair. This pair you are making because you know that you have to sort this pair on the basis of its value. So first is value and next is its index. And then I'll simply sort it. And then I will actually apply this for every element. I'll go on to every element from left to right, which means from smaller to larger element, I will keep on going and keep on updating my bit. And let's say the next element comes in. Let's say 2 comes in. Its index is 1. I will update at location 2. I'll say, bro, count has increased to 1. So I did an update operation. Update the value 1 because I just want the count. That's it. At the index, existing index, which is ID plus 1. Okay, updated. But bro, you are just updating. Where is the answer? You have to find the count, right? And you told me that count is the number of elements to the right. And I know I have been going in the increasing order. So whatsoever count, if I go and find right now, the sum of count in the right side of this specific thing, then I will easily find out how many elements were smaller than me in the right side. I'll go and simply say, bro, give me the range sum from index 3 up till the super end. So he will give me, which means your binary index tree or your Fenwick tree will give you a range sum from index I plus 1 to index n. How you do it? Simply, if you had not remembered how you do it, please go and watch the Fenwick tree video. Simply, we query n, which will give me the range sum from 1 to n, and then we query with ID plus 1, which will give me a range sum from 1 to ID plus 1. And that's how I can simply go and find out, bro, what is the range sum from ID plus 1 to n. and that's how I can simply go and find my answer. So this will become your answer of ID. Again, if you don't understand this, please go and watch the Fenvic tree video. But again, if you are looking for an interview perspective, please go and look for the next part of this, in which we will solve it via another algorithm. Now, for sure, we will just finish it up, wrap it up, that we have 5. Then we will go at the index ID plus 1. We at index 1, just put a count of 1. Okay, because we just want a count. We will find the range sum. For him, the range sum is 2. And that's how you are actually populating your answer itself, which means answer of index 0 is populated with the range sum from ID plus 1 to the end. And let's say last one is 6. Update the index 3, find the range sum, which is 1, and then update the answer of 2 as 1. And that's how you can simply get the answer. So the code is exactly pretty simple, that this is the just small Fenvic tree code. This is the just small Fenvic tree code. If I just go back and show you, this is the only part of the Fenvic, and that's the reason. That's a beautiful part. Code is so short. Again, the entire code I've explained in this video. We will just use as a boilerplate code. Now, as we saw, that we will simply make a bit array for our Fenvic tree. Then we will simply push back elements and the indexes, and then we will sort it. Now, I'll go on to every element in the increasing order. So I'll just simply iterate all the elements, and then firstly, as soon as I encounter element, please update value 1 at this index, because my bit is 1 based, so I'm updating 1 based in my bit. But then I have to also find the answer for that specific ID which I am also right now querying. So I'll just say query of n minus query of ID plus 1. That will give me okay, range sum from ID plus 1 to the super n, which is end. And that's how ultimately I will populating my answer itself, and that's going to be your answer. Now, this is O of n log n because of using of Fenvic tree, and space is O of n because of the bit array which you are making. Now, the code and all that thing you can find here itself. But now this is the easy approach. But it's highly chance, like that's a highly possible that your interviewer might not even know about a Fenvic tree. And usually in companies, people are very just basic DSA persons, so they might not know Fenvic tree. In that case, there is another thing. As you saw in the very beginning, I told you it's a log n factor, right? So I can either use a Fenvic tree or a segment tree or a merge sort or maybe a sorting. Now, sorry, I can use a sorting or I can use a binary search. Now, for sure, when I told the term sorting, why not the algorithm of a sorting, which is merge sort? Now, simple. I use a normal basic merge sort. Aryan, but tell me, how you even got the intuition that you will not use a binary search but a sorting? Because if you remembered, binary search I can use only when the things are sorted. But merge sort is I can try to sort stuff out. I will try to sort, which means while sorting the stuff, maybe I can find my answer. So that is what I will try of doing. So I'll apply a simple merge sort. If you don't know a simple merge sort, it just simply says that you have an array, keep on dividing the array into chunks, and then merge that chunk. Aryan, how is that useful? You will see that part. But yeah, that is the basic merge sort, which means divide it and then keep on merging it. That's the basic idea of merge sort. Simply how you divide it, as you do a simple division in a binary search, that you have your left, you have your right. Now you need to divide it in half. So you need to do a mid. Mid will be, again, simple. You can do a left plus right by 2, but a good practice is to do left plus right minus left by 2. That you have also seen in binary search. Now, when you have seen that, okay, you can do a simple division. Ultimately, remember, what's the aim of merge sort? As this thing says, it's a merge sort. It is a sorting algorithm. So it will try to sort your answer. It can be either increasing or decreasing depending upon what you want. But remember what we want it in decreasing. Aryan, why are you saying decreasing? Because if you remember, we want the count of smaller elements to the right. So we want smaller elements to the right of our value. So we want, again, merge sort can sort in both increasing and decreasing. But now my aim, my responsibility or my requirement is that I will sort it in the decreasing order, because I want the count of smaller elements to the right of the value. So it's the reason I'll do a decreasing order sort. Now, Simple. I got the mid. I can simply do a division now. Now, if I do a division, simple. Again, that's a simple division that the array will break it in a half. This is the two halves. Again, it is not yet reached. It's a very base case. Very base case is single element. So I will again do a division. Again, do a division. Again, you can see the values. Mid, mid. Okay, mid. Again, division. Again, it will break down to two values. Two values. Two values. And then again, now it has reached the very basic value. Very okay, just single value. Now I will apply my actual merge. Okay, I did split it, which means I am applying recursively merge, or like merge sort. But now I will apply a merge algorithm, which means these two. Now they have reached very basic. Now keep on merging them. How I will merge them? Simple. I know my ultimate aim is to sort in the decreasing order. So when I merge 5 and 2, I just want, okay, bigger element should come first. Next is smaller element. So if I want to merge it, I will make a 5 2. But bro, okay, you merged it, but how come you're finding answer with this? Bro, if you remembered that all this, one thing, make sure. One thing you have to remember that all these are the indexes 0, 1, 2, and 3. And as you remembered, you are just splitting that. So you are splitting that. So for sure, order is always maintained. Initially, the order is always maintained. So now when you are merging it, you know one thing for sure. If something is after me, he has a larger index, which means he's actually in the original array after me. So when I'm merging these two, which means when I'm merging 6 and when I'm merging 1, I know, okay, he's after me. I can compare the simple value, bro. Bro, you are 6, I am 1. Sorry, I am 6, you are 1. I'm merging it. I know that I'm merging with you. I know that you are smaller. I can compare the values, right? I can compare the 6 and 1. I can simply compare two values. You are smaller, bro. So for sure, for answer of 6 will increase by 1 because it is in the right. 1 is in the right of 6. So answer of 6, which means whatsoever location would have been for 6, but I'm just saying answer of 6 will increase by 1. If you remember, location of 6 was at index 2 originally. So for answer of 6 will increase by 1 just while merging itself. So while merging, I would easily know. If I know, bro, while merging, I have to compare the values. I will compare this I and this j. So if I compare it, I know I will merge it. Now, if I am merging it again, remember, after you merge, you remember that one fact that things should be sorted. And for me, sorted in the decreasing order. That's a fact. So, and while merging, I figured out that 6 and 1 I'm comparing and merging. While comparing, I saw 1 is less than 6. So for sure, for 6, answer will increase by 1. So for 6, answer increase by 1. And same way, while merging 5 and 2, answer for 5 increased by 1. Now, maybe you might not understood that well. It's just one element merging. How it go about? More simple. Now you will merge 5, 2 and 6, 1. Again, remember the fact, this is in the right portion. For sure. Its index, I'm not saying it could have happened that this would have become a 3 and 2. This again, it could have happened that index would have been 1 and 0. But the fact is that these indexes are for sure larger than all these indexes because they are in the right part. When they will merge, then index can shuffle. But before merging, indexes are always sorted. So now again, please see, this is how the answer is looking like so far. Now when I'm about to merge it, I'll simply say, bro, one thing I know, I have been merging in the things are always in the decreasing order. So this portion is in the decreasing order because every stage of merge sort is a decreasing order because I have maintained everything should be a decreasing order one. So this is in the decreasing order. This is in the decreasing order. I know I'm about to merge it. When I'll merge it, for sure I'll compare two values. I know I want to merge this, which means I want to make sorted array. After merging, I want to make a 6, 5, 2, 1. This is after merging I want to obtain. So how to merge it? Simply compare. Okay, I'll compare my nums of I and nums of j. I'll compare nums of I and nums of j. For sure, you will see that nums of j is larger. So if nums of j is larger, he will come. So usually what happens is in a merge sort is you make a temporary array that whatsoever, okay, you have two small arrays. You will merge that and make a big array. So you make a new temporary big array and then you will try to see what elements fits in this temporary array. So I compared nums of I and nums of j. I figured out, okay, nums of j is more. So he should come first. Because I remembered, maqsad nahi bhulna. I remembered my aim was to make a sorted array like this. So for sure, he will come first. Now, when he will go, then I will compare. Okay, for sure, when he will go, then he will iterate. Okay, now next J will come here. So he will compare I and J now. Okay, for sure, you can see your 5 is more. So 5 will come next. So in the temporary array, you keep on building your answer. How this simply works is, okay, while your I is less than equal to your mid and your J is less than equal to your right. If you remembered, your I is here, left and mid is here. Mid plus 1 and right is here. So you put a new pointers. Okay, I will point to the left array, J will point to the right array. So for me, I's extreme index is mid, for J, extreme index is right. So I just said the same thing. Okay, while my I is less than equal to my mid and my J is less than equal to my right, then I will do one thing. Okay, I have my new array called as temp array, in which I told you it's a temporary array in which I will merge things up. So I'll compare nums of I and nums of J. Whosoever is large, I know nums of J is large, put that in my temp. If the nums of I would have been large, put that in my temp. And that's how you can simply keep on building your merged array in the new temp array. We will see that how we'll assign it back to my nums array. But yeah, this is how you are building your merged array itself. Okay, great. But Aryan, again, one thing, you merged it, but where is the answer? Where is the answer? Like, okay, you merged it, but where's the answer? That's a part that, okay, while merging itself, you saw that 6 and 5 you were comparing. 6 and 5 you were comparing. You saw that, okay, it is nums of J. Nums of J is already in the right. J is in the right. I is in the left. Nums of J is in the right. I is in the left. I'm comparing these two. J, I saw it is more. It is less. So for J, already answer would have, for J, which means for 6, answer would have been impacted only by 1, right? It is already large. So this will not impact my answer. But, and for short, for 5, I want the smaller elements. While my J was a larger element. So for my 5, answer never increased. For my 6, answer also never increased because I was comparing 5 and 6, not 1 and 6. 1 and 6 are already compared. So I'm comparing 5 and 6. The possibility was that, okay, for 5, answer would have increased considering 6 was a small element, but 6 is for sure more than 5. So, which means that I saw one thing, that while I'm comparing my nums of I and nums of J, I saw that if my nums of I is less than equal to my nums of J, then for sure, right side I can simply ignore because right side value is already large. He will not be impacted. And left side, I want smaller element to him on the right side. I found out right side means J. J has larger element. So for sure on the left side also answer will not increase. So in this case, answer will never increase for anyone. But as we saw that, okay, what if, okay, he has gone to the array. Now my J will point here. Now you will see that, okay, your I is pointing at 5, J is pointing at 1. Remember that fact. So, okay, for 5, which is a larger element on the left, J is on the right. I know, okay, because I know I is on the left, J is on the right. So I know for sure that 5 is more than my 1. Oh, 5 is more than my 1, which means my nums of I is more than my nums of J, which means for sure I can tell the impact which 5 will be added. So I'll simply add and say, okay, bro, for 5, I have found one smaller element. But Aryan, are you saying that you will go on? Because it can happen that, okay, I have 0, -1, -2, and -3. Let's say I have more elements because you remember it is decreasing. Things which are merged are decreasing itself. So Aryan, are you saying that I will go and iterate on the entire array? No. I know that this entire thing is decreasing. For sure, if my 5 is more than my 1, so for sure my 5 will also be more than all the element to the right side. So what will happen is that I can simply say for 5, the contribution or the increment in the answer will be nothing but my right minus J plus 1. So if this was my right, this was my J, I know that my nums of I is more than my nums of J. So for my answer of my I'll simply go and say, okay, answer for my 5th index will be nothing but, answer for my 5's index will be nothing but my right minus J plus 1. All these numbers are actually smaller than my 5, and that's what I wanted also. All the numbers which are smaller than my element, and that's how I can simply get that answer also and then simply merge it. So in this case, you will see that 5, you have just one element which is smaller, so you will add a contribution of 1 for your 5. And that's how you can simply keep on merging and finding the answer parallelly. Now the code is pretty simple, exact same stuff. Firstly, we will make the vector of pair. We will now simply not sort it, but we use a merge sort to sort it and find the answer also. So I'll have my answer and I will pass that answer as an address in my merge sort function. Now you will start off from simple. You remember this is left, this is your left, this is your right, and then you will keep on merging it. Now simple merge sort. If your left is less than your right, then simply find the mid. As you remembered, now it's a simple recursion that you will find the mid, and then you will ask a recursion, bro, solve from left to mid and solve from mid plus 1 to right. That's what you are doing. Now when the split is done entirely, when you have got your very basic, very narrow level, just one element, then you will keep on merging it. So whenever any function is after the recursive call, so firstly recursive call will happen entirely deep, very deep. When it will come back, then this function will be called, which is the merge function. Now the merge function is our main crux for us. What's the merge function? Merge function simply says one thing, bro, get me, you have left, mid and right. So I know one thing for sure, that left to mid is one array and mid plus 1 to right is other array, and then I just know I have to merge these two arrays. So he'll do the exact same stuff. I know that I make a temporary array which will be of the size right minus left plus 1, because if you remember, one array is from left to mid, other array is from mid plus 1 to right. Ultimately, after merging, the array will be of size left to right, which is of size right minus left plus 1. Now when you will be simply doing a simple what we saw in the code also, while your I is less than equal to your left, again remember this code portion which we saw, that while your exact same code, I'll just copy paste that. Okay, while my I is less than equal to my mid, simply compare the nums values, nums of I. If it is less than equal to my nums of j, then in my temporary array which I have built, I'll simply push back the nums of j. Higher value I will be pushing back. Same way, I'll do same stuff. Else, which means if your nums of I is more, then simply say in your temp nums of I will go away. But if you remembered one thing also, that if your nums of j is more, no worries at all. But if your nums of I is more, then I will be also adding the impact in my answer. What's the impact? Impact is right minus j plus 1. So I'll simply come back and say the impact in my answer will be right minus j plus 1, and that's the impact I will be adding. Now let's say if you're merging two arrays, let's say, okay, one is a very big array, one is a small array. So when this array is finished, for sure the remaining part of a big array, you will still have to put it in the temporary array. Let's say this is a temp array. So right now you are comparing I and j, but what if one of the element is finished, one of the arrays is finished, then still you have to find the entire merged array, right? So okay, if my I is still remaining, then merge it. Else, if my j is remaining, then simply merge it. So now your temporary array is built, which is the merged array. Now Aryan, okay, that seems good, but you saw that it is your temporary array, not your main array. You have to populate, or you have to sort your actual array, because if you remember, if you say a sort function, sort of nums dot begin and nums dot end, dot end, so this sorts your actual array itself, not a new temporary array. That's the reason I will do exact same stuff. I will assign this temp value, which is already a sorted array, sorted portion of the array. I'll assign it back to my nums, which I have been passing as an address. You will see passing as an address, and that's how I will assign, because I remember this temp array is sorted. So I'll just simply assign that sorted portion for, I know also one thing, that temp array is from left to right. So I'll properly assign the indexes and just say, bro, this is my sorted array, and that's how I can simply do a sorting of my array. This is the only portion which we added in our merge sort. Again, the rest of the portion is the code of merge sort itself. So by this problem, you learn Fenvic tree, you learn merge sort, and then you also learn this problem itself. This portion, this portion is entirely merge sort. This entire question is merge sort itself. The only extra line added is this line. That's it. That is it to get you the final answer. That's it. I hope that you got it. See you. Goodbye. Take care. Bye bye. Cheers.